Hello, everyone. Welcome back to the ILTA Physics online lecture series. Today, we're going to dive into the concept of angular acceleration. As you can tell from the title, acceleration, we'll be talking about the motion of objects where the rotational speed is actually changing. Up until now, we've mostly focused on uniform circular motion, where an object rotates at a constant speed. But today we're going to learn about the kinematic relationships like position, velocity, and acceleration for objects that are speeding up or slowing down as they spin. First, we will learn the properties of angular acceleration, which is defined as the rate of change of angular velocity. Then we'll look at the relationship between angular velocity and angular acceleration, specifically looking at it from a kinematic perspective to see when rotation speeds up and when it slows down. Once you understand angular acceleration, you'll have covered all the kinematic parameters for non-uniform circular motion. We'll wrap up the kinematics part of rotational motion by comparing it with linear motion. We're already familiar with the kinematic formulas for linear acceleration, so I'll put those side by side with our new rotational variables, including angular position, angular velocity, and angular acceleration in a single table. Finally, we'll look at how the angular acceleration of a rotating object relates to its actual physical moving speed, which we call tangential velocity and tangential acceleration. This tangential motion can be thought of as the linear component of circular motion at any given instant. We've covered quite a few different types of acceleration while studying circular motion, haven't we? Centripetal acceleration, angular acceleration, and tangential acceleration. So, in today's lecture, I'm going to break them all down and clear everything up so you can see exactly how they all fit together. Alright then, let's quickly review what we covered in the last session. Last time, we introduced angular kinematics to describe the movement of rotating objects. First, let's look at the close relationship between rotational motion and circular motion using the diagram below. We can say that an entire object spinning in place around an axis is undergoing rotational motion. However, if we model this as an extended body, we can think of each tiny part of that object as undergoing circular motion around the axis. So the rotation of the whole object is really just the sum of the circular motions of all its small parts. Based on this understanding, we can easily represent the position of an object in circular motion using an angle, which we call angular position. Remember, the unit for angular position is in degrees. It's the radian, which is defined as the ratio of the arc length to the radius. Since it's a ratio of two lengths, it's a unitless quantity. In our daily lives, we usually use degrees, but we found the relationship between degrees and radians through a full circle. 360 degrees is equal to 2 pi radians. Now that we've defined angular position for a rotating object, we can define its velocity. If we know the position, we can calculate how much that position changes, called displacement, over time interval. In circular motion, we refer to this rate of change as angular velocity, and it can be expressed with the following formula. If we express angular velocity using the period and frequency of the circular motion, it looks like this. One thing to be careful about: angular velocity is NOT, the distance traveled divided by time. Make sure you accurately understand it as the displacement of angular position divided by the time interval. Also, both angular position and angular velocity are vector quantities with both magnitude and direction. We've defined counterclockwise rotation as the positive direction of a motion. Finally, the magnitude of angular velocity is called angular speed, and it's commonly used to show how fast an object is spinning. We use the term tangential speed to describe the instantaneous linear speed of a particular point on a rotating body. The relationship between angular speed and tangential speed carries a very important physical meaning. If we derive the relationship based on one full revolution, we find that tangential speed is the product of angular speed and the radius, which is the distance from the axis, as shown in the formula below. This is the quantitative result of a key physical phenomenon. While every part of a rotating disk has the same angular speed, each point on that extended body has a different tangential speed. In the diagram below, points A and B are on the same line from the axis, so they have the same angular speed. However, point A is moving faster tangentially because it is further from the center. It has a larger radius. All right, now let's use this foundation to study angular acceleration. Up until now, we've assumed uniform circular motion, where the angular velocity is constant over time. But if a rotating object spins faster and faster, meaning there is a change in angular velocity, we define the rate of that change as angular acceleratio. You can think of this as having the exact same physical meaning as the acceleration we defined in linear motion. Linear acceleration is the change in velocity divided by the change in time, as shown in the formula on the right. Similarly, angular acceleration is the change in angular velocity over time. In other words, angular acceleration tells us how much the angular velocity of an object in circular motion is changing. It's important to note that this new angular acceleration is a different quantity from the centripetal acceleration we learned about earlier. To recap, centripetal acceleration is the acceleration that creates the center-seeking force, called centripetal force, that keeps an object on its circular path, as shown in the diagram on the right. In terms of physical meaning, you could say centripetal acceleration is more about the kinetics, which is related to forces, while angular acceleration is about the kinematics, description of motion. Now, let's look at how angular acceleration actually changes to the angular velocity of an object. We said angular acceleration represents the change in angular velocity. Depending on the relationship between the two, the object might spin faster or slower. What we really care about here is the direction, or the sign of both angular velocity and angular acceleration. I'll give you the conclusion first. If the angular velocity and angular acceleration have the same sign, the object speeds up. If they have different signs, the object slows down. This is exactly the same as what we learned for linear motion. Let's look back at linear acceleration for a second. Looking at the motion diagram for an object in linear motion. In the first figure, for an object moving from left to right, we determine the direction of motion by the velocity arrow. In this case, if the acceleration is also from left to right, the same direction as the velocity, you can see the object speeds up. Its velocity increases. In the second picture, if the velocity and acceleration are in opposite directions, an object moving to the right will gradually lose speed. This is deceleration. If we think about this just in terms of the signs of velocity and acceleration, it looks like this. Having the same sign means speeding up, while opposite signs mean slowing down. I'll let you think through the other cases on your own. Now, let's head back to circular motion. The diagram below shows 4 different cases for an object in non-uniform circular motion. The first image is a motion diagram of an object spinning counterclockwise and speeding up. The second image shows it spinning counterclockwise but slowing down. In both cases, the direction of circular motion is determined by the sign of the angular velocity, which is positive here. Just like in linear motion, if the signs of angular velocity and angular acceleration are the same, it's accelerated circular motion, called speeding up. If the signs are different, it's decelerated circular motion, called slowing down. By the same logic, let's look at an object spinning clockwise. The third and fourth graphs represent this, which we know because the sign of the angular velocity is negative. In the third case, the signs are different, so it's slowing down. In the fourth case, the signs are the same, so the rotation is speeding up. To repeat, the exact same physical laws apply here as they did in linear motion. Having the same sign means speeding up, while opposite signs mean slowing down. Now, I've organized everything we've discussed regarding kinematics into a single table. I want you to compare the corresponding kinematic variables for linear and circular motion. You can see that the familiar variables, position, velocity, and acceleration, correspond to angular position, angular velocity, and angular acceleration in circular motion. I've also listed the formulas connecting these variables below. Compare the equations for uniform motion and accelerated motion for both linear and circular cases. While we didn't derive every single rotational formula in this lecture, you can derive all of them using the same methods we used for linear motion. For now, we'll skip the derivation process. I just want you to remember the resulting formulas by comparing them to the linear ones you already know. One thing that makes circular motion a bit more confusing than linear motion is that velocity and acceleration appear in multiple directions. Organizing these directions properly is the most important foundation for analyzing circular motion correctly. When analyzing circular motion, remember these three specific directions. First, centripetal direction points toward the center of the circle. This is the direction of centripetal force and centripetal acceleration. This comes up mostly when we look at circular motion from a kinetics perspective, which is all about force. The second, rotational direction, the path along the curve of the circle. This is where we define angular position, angular velocity, and angular acceleration. This is key for the kinematics perspective. And finally, tangential direction. This is always perpendicular to the radius at any given point. This is where tangential velocity and tangential acceleration are defined, representing the actual instantaneous speed of the object. We analyze this by looking at a tiny segment of the circular motion and treating it just like linear motion. The names of these three quantities give you a hint about which direction they belong to. So just make sure you can distinguish these three directions clearly. Finally, let's look at tangential acceleration for a rotating object when its speed is changing. Like any definition of acceleration, tangential acceleration is defined as the change in tangential velocity divided by the time interval. Using the relationship we derived earlier, we can express tangential acceleration as the product of angular acceleration and the distance from the axis. Compare this to the definition of angular acceleration, change in angular velocity over time, to see how they relate. The diagram below shows a motion diagram with the velocity and acceleration at each position. On the left, we have constant secular speed, meaning angular acceleration is 0. Since there's no angular acceleration, the rotational speed, called tangential velocity, is the same at every point, and the centripetal acceleration is constant. Remember the relationship between centripetal acceleration and tangential velocity. Now look at the right side where the rotation is speeding up, called accelerated circular motion. Since the angular acceleration is positive, the green arrows representing tangential velocity get longer and longer. Consequently, there is a constant tangential acceleration present. Also, because the tangential velocity is increasing, the centripetal acceleration must also increase proportionally. Physically, this means that to keep an object on a circular path as it gets faster, you need a much stronger centripetal acceleration and thus more force. Finally, I want you to take a close look at these three accelerations in the three different directions we've discussed. Make sure you understand what each physical quantity represents, and be sure to memorize the formulas as well. That's it for today's lecture. Great job, everyone. See you next time.